In Module 2, we'll be looking at TensorFlow Lite models, and these are models that can be deployed on the edge. In this tutorial, we'll be looking at how to convert the TensorFlow models that we've been designing in Module 1 to TFLite models. So the first thing we'll be doing is importing all our necessary libraries. And we'll be looking, just as an example, at the simple regression problem that we dealt with in tutorial 1 and 2. So we'll be modeling y equal to 2x plus 3 using dense layers. So we define our layer as a dense layer with only one neuron. We define our optimizer as our stochastic gradient descent and our loss as mean squared error. And then we go ahead and compile our model. We also define our very simple data set of 6 points or 6 data samples. So we have our x's and we have our y's. And this essentially becomes our training data set. So, and the next thing we do is just train our model on these x's and y's, and we train it for 500 epochs. And this should happen fairly quickly. After we do that, we're just going to predict x equal to 10, and just to verify that our train model is doing pretty well. So we use the model.predict API. This should be familiar with you guys. And yeah, so we're going to run model.predict on 10, and we see that we get 23, which is very close to what the expected answer is. And we also look at our parameters or our learned parameters. We see that our weight is learned as 2, which is good. And our bias is 2.98, which is very close to 3. Okay, so this is our simple TensorFlow model. What we're going to do now is we're going to save it onto disk. So a reason you would do that is because if you're running multiple sessions or if you train your model and your session crashes out, you have the saved model and you can just download it to your local system. In that way, you wouldn't have to retrain your model all over again. So you can take the saved model and do any sort of post-processing or even run inference in a different session. So you could come back tomorrow maybe and just run inference with your same model. So you could load back your same model and run inference. So that's an advantage of saving it onto disk. So just define your path and use your tf.savemodel.save API to save it onto your disk. An important note here though is once you run this, you should see the saved TFLite model here. Sorry, the saved TensorFlow model, my bad. And it'll be saved under savemodel.pb. And essentially your TensorFlow models are saved as protobufers with the extension pb. So download this directory onto your local system because even this directory is running on the session. So if your session crashes, it might disappear from the left panel. Okay, so now that we have our TensorFlow model, we're going to convert it to a TFLite model. And it has, there are just 2 steps to do this. So one is instantiate a converter object, and it's of class TFLite converter. And we're going to link it to our TensorFlow model, which is at this path defined by export directory. So you're going to use tf.lite.tflite converted from saved model because our TensorFlow model is saved now. And we pass in the path to this TensorFlow model. And the next step is just doing a converter.convert. So using the convert method, and it converts your TensorFlow model at this path into a TFLite model. Now this TFLite model is running on the session. So again, naturally, we're going to save it onto disk. So to do that, we again define our path. The TFLite models will be saved with the extension .tflite. So now we have our path of our TFLite model. We're going to use the TFLite model file.write bytes API to link or essentially write all the contents of our TFLite model that we've converted here and write it into this file. Okay, so we're taking the TFLite model that's on the session, and we're going to write it into the TFLite model file, which is the path defined in this cell. Yeah, and this write bytes API also gives us the information of how many bytes has been written into this file. So our TFLite model is now of 1080 bytes. Okay, so question 1, why do we convert our TensorFlow model to a TensorFlow Lite model for edge devices? So two reasons. One, we're obviously trying to compress our model so that it can be deployed onto smaller resource-constrained devices. And second, it also converts it into a form conducive to further optimizations or pruning, quantization. It just converts it into a form that allows that. So that is your answer to question 1. Okay, so now we have our TensorFlow Lite model. And we've said that there is some sort of compression and changing of parameters to allow it to be allow it to run on edge devices. So what we're going to check, we want to check if the accuracy is persistent, that the accuracy does not drop. So we have to run inference. Ideally, since these TF-Lite models are meant to be run on hardware, you would run or test it on hardware. But TensorFlow provides an interface called called interpreter that allows us to run inference. Okay, so that's what we're going to do here. So we're going to run inference, but on this collab session. So similar to converter, we're going to define an instance of the interpreter class, and we're going to link it to our TF-Lite model. So that's our interpreter. After this, there are a couple of steps. So the first thing is we're going to run interpreter.allocate tensors. So this essentially is telling the interpreter to pre-allocate some tensors that correspond to our TF-Lite model. And this essentially is done by TensorFlow to allow for some optimization, further optimization tricks. So what we're saying is that we have some pre-allocated memory for our model. And once we run allocate tensors, the interpreter is going to go through that memory, allocate memory space, and allocate it to all the tensors that correspond to our TF-Lite model. So for example, our inputs, our outputs, our weights, and so on. Okay. So next we get our input and output details. So interpreter.get input details and interpreter.get output details. And when we print them, there are some important details. So a few being the D type, for example. So the D type of our expected input and the output that our interpreter is going to produce. Another important detail would be probably the shape. So here we say that they are scalar values. But more importantly, it gives you these index details. So index 0 and index 3. And what these indices mean essentially is that your input, okay, so let's think about interpreter as sort of an array. And at index 0 of this interpreter array, you would feed your input value to be predicted. Okay, so the value that you want to test out, for example, say 10, has to be fed into index 0 of this interpreter array. Okay, the interpreter then runs inference, and then at index 3 is where we would be able to read our output or our predicted output from. Okay, so that's what these indices mean. This cell would make it clearer. So let's define a value to be predicted. So let's take 10 and convert it to a form that the interpreter requires it to be. So that's defined by our shape as well as the D type information that we saw here. So to predict is in the right form. The next thing we do is we take this to predict value and we feed it into the right index, which is defined, that is index 0 here, okay? And we do that using the set tensor API. So essentially, we are feeding the value to be predicted into our interpreter at this defined index using the set tensor API. Next, we run the interpreter.invoke, which is running inference. In other words, it's applying our model onto this value to be predicted. Okay. It's similar to model.evaluate or model.predict, basically. And the next thing we do is we know that the predicted output is going to be at this defined index. That's index 3 here. And we're going to read it using our getTensor API. So we're going to read the output or the predicted output using getTensor API from this index of the interpreter and feed it into our TFLite results variable. And when we print it, we see that it is very close to what the predicted value should be. So question 2, list any 2 reasons why we require the model input and output tensor details. So one would be to get the D type. So the data type of the expected input and the output. Another one would be the shape. So are you feeding scalars or vectors, and what are their respective shapes? And more importantly, the indices at which you would feed your input data to be predicted and read your output predicted data from. So those are some of the reasons why we would require the model input and output tensor details. And finally, this is the same thing, but we can test it out with just another sample example. So just change your 10 to 5.5. Everything remains the same. We set the tensor. We set this value into the right index. We invoke inference, and we read the predicted value. And we see that it's very close again to the expected value.